Today in Chem 100, we're going to review for the exam that's due next Thursday. This is Tuesday, the 18th of February, and on the 20th of February is when exam 3 is due. This material, as usual, comes from the review document, and I've highlighted the ones that I want to be sure and get to. So let's get started. All right, number one. The number of grams in 2.58 mole of sodium carbonate is. What are we given? We're given 2.58 grams. And the question is, excuse me, 2.58 mole. And we want to find out how many grams. All right. This is a dimensional analysis problem. To go from moles to grams is a simple one-step conversion factor. Remember, the denominator has where you're going. The numerator has where you're going. The denominator has where you've been. Right? And that means since you see grams and moles in a quotient, that's always molar mass. So we need the molar mass of sodium carbonate. Well, can you get the molar mass from the name? No. It's not possible. That's why I insisted so early on that you learn how to write compounds from their names. Sodium carbonate. This is sodium. And carbonate is not on the periodic table. Carbonate is a polyatomic ion that you can find in useful information. Sodium is an alkaline metal with always a +1 charge when it's in an ionic compound. And carbonate is a 2- charge. So we simply balance the charges. This is a type 1 compound. In other words, the metal has a fixed charge. So we need 2 of these. 2 pluses balances that 2 minus. Okay. Now we got our compound name. We can calculate the molar mass to fit in our conversion factor. So go to your periodic table, look up sodium, 23.00 grams per mole, and we have 2 of those. Then we have 1 carbon, and we have 3 oxygens. All these values come right out of the periodic table. Okay. So now you'll need your calculator. 2 times 23 is 46, and then 12.01, and then 3 times 16 is 48. That's 106.01. 106.01 grams per mole. 106.01 there. So all we have to do is multiply that value times this number, because numerator, denominator leaves us with the correct units. And my calculator tells me 273.5058. Okay. How many significant figures can I keep? This is a multiply divide rule. This is the only one that matters. That's an exact number. So it's 3 significant figures equals 274 grams. Okay. That's why D is the answer. All right. I went through this one in nauseating detail because if we encounter one of these again, this type of problem again, in a subsequent problem, I don't want to have to slow down. You're going to see me do things and you'll know why I'm doing them because I've already shown you here. All right, that was number one. Number two. 8.52 grams of water contains how many moles of water? Molecules of water. 8.52 grams of water. Okay. This is, again, a dimensional analysis problem, but it's a multi-step because we don't have a conversion factor that goes from grams to molecules. But we do need to go from mass to numbers, and that's molar mass. Okay, and we've calculated this one before. 18.02 grams per mole is water. Now that we're in numbers, we have a conversion factor for moles to numbers of molecules. All right, so we need to get rid of moles here, numerator, denominator, and 6.022 times 10 to the 23rd molecules. Avogadro's number. There. That's the thinking part. The rest is just number crunching. So 8.52 divided by 18.02 times 6.022 times 10 to the 23rd is 2.8475 times 10 to the 23rd. And how many of these digits can I keep? This is the determining number of significant figures. That's an exact number, that's an exact number. So we're limited to 3. That means here, 0.85 times 10 to the 23. Okay. And that would be A. All right, number 3. How many moles of Al2O3? Right. Al2O3. How would you name that compound? Normally, we wouldn't say how many moles of Al2O3. If we know how to name it, what kind of compound is that? Type 1, 2, or 3? Well, it's not a 3 because there's a metal in it. But is that metal fixed charge or variable charge? Aluminum is fixed at 3 plus, 2 minus. So you see that we get the balance. But this is aluminum oxide. That's it. That's all you need. It's unambiguous and it's non-redundant. We don't have to say the charge because it's always 3 plus. Okay, now to the problem. How many moles are present in 78.8 grams? So if we have 78.8 grams of that compound and we want to convert it to moles, again, it's molar mass. Okay, so 2 times aluminum. Look up aluminum, 2698 grams per mole. Okay, and 3 times 16 for oxygen. Okay, now we can find out what the conversion factor is. 26.98, 2 times, and 48. 3 times 16 is 48. So this is 101.96. Okay, just divide that into 78.8. And I get 0.772852. Three significant figures, 0.773. Okay. That would be A. All right. So clear the board. And do number 4. All right. Which of the following compounds has the greatest percent by mass of oxygen? All right. You know how to calculate percent by mass when you have the formula, but none of those A through E have the formula. So we got to write the formula for each one of those compounds, then calculate its percent by mass. Okay. This is where Henry Ford's assembly line is useful. So we got A, B, C, D, and E. The first one, potassium carbonate. Type 1 compound. Potassium is an alkali metal. It's a +1 charge. And carbonate is a polyatomic ion with a 2- charge. So we need 2. There's potassium carbonate. Nitric acid. Notice that it doesn't say hydro. So we look at nitric. Where does nitric come from? X come from 8. So nitrate is the polyatomic ion, and then hydrogen goes here. That's nitric acid. Of course, in aqueous solution, but we don't need the aqueous to do our calculations. Zinc 2 oxide. That's a type 2 compound because zinc 2 tells us that we have a charge that must be specified. We can also look at the periodic table and see, all right, zinc is one of those in the transition metals that necessarily has multiple charges possible. So zinc 2 oxide says zinc and then oxygen 2-. That's all we need. Just one of each. Balance the charges. How about D? Sulfur dioxide. Sulfur and oxygen are both nonmetals. This is a type 3 compound. And the other giveaway is we say dioxide. That means 2. So we have sulfur and 2 oxygens. And the last one is also a type 3 compound, diphosphorus pentoxide. Okay. So now what we need is the molar mass of each one. Okay, the molar mass of K2. Well, let's see. Percent mass by oxygen. So 3 times 16 is 48. That's for the oxygen. 48. 16. 32. Right? 2 times 16. 5 times 16 is what? Right? Excuse me. That's not right. 5 times 6 is 30. And 3 and 5 is 80. So this is 80. There we go. Now the rest of the molecule, in this case, is carbon, right? 12.01. And 2 times potassium, which is 39.10. 39.10. Okay. So if we add those together with 48, we'll get the denominator. All right. 48, 12.01, and 39.1 times 2. Add that in there. 138 point. Yep, 138.21. Okay. That'll give us the percent mass for oxygen times 100. Well, see, I've already got it in here, so let me go ahead and do the calculation. That's 34.7% oxygen mass. Okay, how about this one? Here we have the oxygen already. Now we need to add the nitrogen, which is 14.01, and hydrogen, which is 1.01, plus 48. That's 6302. 63.02 times 100. And that's 76.2 oxygen by mass. Then we have zinc added to oxygen, and zinc is 6538 plus 16. That's 8138, 81.38 times 100. So we divide that into 16, and I get 19.7. Okay. Just keep going. What's sulfur? Sulfur is 3207. Okay. Plus 32. Which is 64.07. That's 49.9. Okay. And last, we have oxygen here. We need 2 phosphorus, 30.97. Right, plus that value. So 80 and then 30.97 times 2. Add those together, I get 141.94 times 100. And I get 56.4% mass. Okay, so now we can compare them and say which one has the greatest percent mass oxygen, and that's nitric acid, 76.2%. I know that was a lot of work. That's why I like to set it up like an assembly line. We're doing the same type of calculation over and over and over again. We just need the correct numbers to go in the calculation. All right. Go to board. And for number 5. All right. Compound X2Y, so this is a hypothetical compound, is known to be 60% X by mass. Calculate the percent Y by mass of the compound X2Y2. This problem is governed by, getting the answer is governed by the law of definite proportions. So we know that with X2Y, we have 60% X by mass. 60% X by mass. So what does that make Y? Y has to be 40%, doesn't it? 40% Y by mass. Now we want to find out what's the percent Y by mass for the compound X2Y2. Okay. Let's see. The ratio by mass is fixed for this compound. It's 6-4 or 3-2. The ratio by, well, while that's true, it doesn't help us much unless we go by mass. If we have 100 grams of the sample, that means this is 60 grams and this is 40 grams. Then if we have 60 grams again over here, right? Now we have two of them. Now we have 80 grams of Y, right? So what would be the percent Y? It would be 80 divided by the total, which is 140. Okay. Times 100. So I get 57%. Why? That's why it's D. We couldn't make the jump from here to here using percent because percent is relative to a compound itself. But if we assign masses to each one, then when we double, we have a 40 grams here, we double the mass here, but we have the same mass here. That's how I made the transition from one to the other. Okay. Number 5, we're going to skip a few repetitions and move down to number 12. What is the mass of 5.826 moles of calcium hydroxide? All right. 5.826 moles. 5.826 moles of calcium hydroxide. First of all, is that correct? Well, calcium is a fixed charge. It's 2+. Hydroxyl is a polyatomic ion with a 1-. So yeah, that's why we have parentheses. You always have parentheses around a polyatomic ion if you need more than one. Okay, so the formula as written is correct. Now what we need is to convert the number of moles to the number of grams. What's the mass? And we look at the answers, and all the answers are in grams, so we know that's where we need to, that's where we're headed. Grams. Okay, we need moles on the bottom to cancel and grams on the top. That's molar mass. So molar mass for calcium is 4008 grams per mole. 2 oxygens and 2 hydrogens. And all these, you look all these up in your periodic table if you don't have them memorized. Then we pull out our calculator and crunch some numbers. That's 74.02 grams per mole. All right, grams on the top, moles on the bottom, so that they cancel and leave us with grams. 5.826. Okay. I get an answer of 4 0.312405 times 10 squared grams. Let's see, our answers range. So how many of these can I keep? Well, we have 4 significant figures, so I can keep it up to there. 4.312 times 10 squared grams is also 431.2 grams. So we look for the possibility. And if I didn't make a mistake, let's see, 2, 32. I did make a mistake. Didn't make a mistake. This should be 40.08. Yeah, that's a mistake. 10 times 5.826 is 431706. 431,706 times 10 squared. Rounded up 4 places. 4.317 times 10 squared, or 431.7. There you go. So that's A. All right. Number 13. Choose the pair of compounds with the same empirical formula. All right. Remember what empirical formula is. Empirical formula is the simplest whole number ratio of elements in a compound. It's not necessarily the molecular formula, but it is the simplest ratio, which means you need the same elements. When we're doing the comparison between the two, you need exactly the same elements in both formulas. And one of them must be a whole number multiple of the other one. So we look at our possibilities. A, does it have the same elements? Hydrogen and oxygen, yes. But one is not the whole number ratio of the other one. So A is not it. How about B? C2H2 and C6H6. Yeah, that's a good candidate. This is the simplest version of that one, and we just need to multiply by 3 to get this one. Okay, so B is a good answer. And we don't have any wonky ones in there. All right, to say one of the above, none of the above, 2 of the above, that type of thing. So we found the answer with B. If you go through the others, you're going to find that there's a combination of either not whole number multiples or the wrong combination of elements. But we found our answer. All right. Number 15. What's the molar mass of barium hydroxide? Okay, first of all, is that correct? We know where barium comes from. It's an alkaline earth, which means 2 plus charge. That's a -1. Yeah, so we've got a balance. Now, the purpose of this problem is to be sure that you know that when you have a subscript on a parentheses, it propagates through to each one of the elements. So for barium, 137.33 grams per mole. Oxygen, we need 2. And hydrogen, we need 2. Okay, so we add those together. And we get 171.35. 171.35 grams per mole. That's A. Now you may wonder why we're spending so much time in this chapter on calculating molar masses. Because when we get to balanced equations and we're trying to determine, if we start off with a certain mass of reactants and we end up with products, we've got to know how to convert grams to moles. And that'll become evident when we get into balancing equations. All right, number 16. Calculate the number of molecules in 0.0004000 grams of what? Gaseous oxygen. This tests your knowledge of the diatomic elements. Oxygen is diatomic. As a gas, that's it. If you don't know that, then you cannot solve this problem. Or if you do solve it, you get the wrong answer. And the way multiple choice questions are set up, usually the person that creates the question understands where the mistakes could be made. And they make the mistake, do the calculation, and that becomes one of the answers. So if you calculate it wrong, you may find your answer there, but it's the wrong answer. So, number of molecules. If we've got mass, we've got to convert to moles first. So grams here, moles there, right? 32 grams per mole is gaseous oxygen because each oxygen is 16 grams per mole. We have two of them. Now that we've got rid of the grams, to answer the question, we need the number of molecules. So here we can go again with Avogadro's number. 6.022 times 10 to the 23rd molecules. Okay. Now we can crunch some numbers. 0.0004 and 32 and 6.022, that's 0.23 times. So my calculator tells me 7.5275 times 10 to the 18th. How many significant figures in this number? 1, 2, 3. These are not significant. These are significant because of that decimal point. So we have three significant figures, 7.53 times 10 to the 18th. Molecules. And that would be D. Okay? All righty. Number 16 is history. Number 17. .6 grams of copper represents how many moles? All right. Grams of copper. And we want to convert to moles. That's fairly simple. All we need is the molar mass of copper. Right? So we look at our periodic table, 6355. Like that. Divide that in, let's see, that's about a third, isn't it? Yeah, that's about a third. Which one of those answers comes close to a third? 0.33, 0.356. So 0.356 mole should be your answer. If you do the calculation, go ahead and do it. I just estimated and looked at the possible answers, and that's the closest one. This one now. All right, calculate the number of moles of Cl2 molecules. That's a diatomic element, chlorine, just like hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, all diatomic. The number of moles of Cl2 molecules in a sample that contains 7.380 times 10 to the 25th molecules. All right, so we're starting out. Actually, in this case, we don't need to know that it's chlorine, right? That's superfluous information. If we know how many molecules and the answer we want is moles, there's only one conversion factor for all molecules, 7.380 times how many? 10 to the 25th molecules. Okay. We want to get rid of molecules and leave us with moles, right? For every 1 mole, we have 6.022 times 10 to the 23rd molecule. So we just divide this by that, and we should get 122.6 moles. Let me do that just to be sure. 7.380 exponent 25, and then 6.022 exponent 23 divide. So I get 1.2255 times 10 squared. And we have 4 significant figures. We can knock it off there. 1.226 times 10 squared. And if our answer is in standard notation, which it apparently is, we move this decimal to the right 2 places, 122.6 moles. That's why the answer is C. All right. Number 22. Acetylene gas is 92.3% carbon and 7.7% hydrogen by mass. And its molar mass is 26 grams per mole. What's the molecular formula? All right. Remember how to do this. You need the percent by mass of elements in a compound to give you the empirical formula. Then you need the actual molar mass of the molecular molar mass to ratio and obtain the molecular formula. So it's a multi-step problem. Now we have 92.3% carbon and 7.7. And let's separate those a little bit. 7.7% hydrogen. Remember, the first problem you have with percent is it is a dimensionless number. You cannot convert percent to anything useful unless you know that it's percent by mass. This is parts per 100, grams per 100 grams. So if we take a sample that's 100 grams sample, this has to be 92.3, not percent, grams of carbon and 7.7 grams of hydrogen. Now we can work with it. We want the mole ratio of these 2 elements. So we have to convert them to moles. Grams on the bottom, moles on the top. Okay? For hydrogen, it's 1.01 grams. For carbon, it's 12.01. Okay? So our first calculation tells us the mole ratio of the 2 elements. 7.685. Let's see. 7.69 moles of carbon. And 7.7, enter 1.01, divide 7.62. All right. Normally what you would do is take the smallest one and divide it into both. But these are so close together, the ratio is approximately 1 to 1. So the empirical formula is CH. What we want is the multiplier. Okay. So next thing you do is determine the empirical weight for that formula. 12.01, 1.01 is 13.02 grams per mole of this formula. The molar mass is given as 26 grams per mole. Ratio the two. That's 2. If this equals 2, then the formula for acetylene must be HC2H2. Okay? That's how it's done. Okay, here's another one that's going to test your ability to write the formula for a named compound. So for 24, we're going for ammonium phosphate. Those are both polyatomic ions. So we treat them as if they were type 1 compounds because there's no variability in the cation charge. Ammonium is this with a +1 charge. And phosphate is this with a 3- charge. Okay? So all we have to do is balance the charges. We need 3 positives. Like that. NH4 taken 3 times PO4. Now the molar mass is 3 times nitrogen and 12 times hydrogen. 1 phosphorus, which is 3097, and 4 oxygens, which 16 each. There we go. So now we crunch some numbers. And 4 times 16 is 64. So I get 149.12 grams per mole. And E is the closest one. Multiple choice test taking technique. If you're off by a few decimal points, pick the best answer. As long as they're not 1 of the above, 2 of the above, none of the above, that type of thing. As long as every answer is unique, pick the best one. And that's the best one. There was some rounding error, either in mine or in the creator of the problem. All right. Skip a couple and go down to 27. 26.4 grams of nickel represents how many atoms? Okay. 26.4 grams. 26.4. This is the dimensional analysis problem, and that's nickel. We want how many atoms? So first of all, we have to convert to moles. We've got to go from mass to some representation of numbers. And the only conversion factor that gets us there is molar mass. Right? So for nickel, that's 5869. Okay, grams are gone. Now we can convert moles to atoms. 6.022 times 10. Okay. I'll calculate it since we got time. 58.69. 6.022 10 to the 23rd. And I get, my calculator says 2.70883 times 10 to the 23rd. We're limited to 3 significant figures. That's right here. So that's 2.71 times 10 to the 23rd atoms. And that would be B. Be your answer. Okay. Next on the agenda, 31. What is the mass of 8 atoms of copper in grams? Okay. This seems like a hair puller, but really it's just a dimensional analysis problem. You have 8 atoms of what? Of copper. And we want to end up with grams. So how do we get there? Well, you've got numbers, but you don't have the right unit for numbers. You need moles to get from moles to grams. So first of all, we have to convert to moles. This is atoms in the numerator, atoms in the denominator per mole is Avogadro's number. Okay. Now that we've got moles, we can convert to grams. We just need the molar mass of copper, 6355. Okay. So let's say 8 atoms and 63.55 times and divide by 6.022 to 10 to the 23rd. And each atom should weigh, and this is, yeah, that's right. Of that number of atoms will weigh this value, 8.44238 times 10 to the 22nd. Right, we only have one significant figure there. Actually, this is a counting number. It's an exact number. So we can keep as many of these as we want, right? Let's just arbitrarily, we'll cut it off here. 8.44 times 10 to the 22 grams. Okay, and that's why B is the best answer. You know what? Minus 22. There we go. That didn't seem real, right? 8 times 10 to the 22nd grams. Those are some big atoms. No, it's 10 to the minus 22 grams. How about, let's see. I skipped that one. I found out later that this involves information that you haven't been given yet. That problem 42 would be an unfair question. But I'd already written out the worked problems, so I just had to, rather than write them all out again and adjust the sequence number, I just X that one out. Number 43. Seven 7.98 moles of sulfur trioxide molecules contains how many oxygen atoms? All right. First of all, we need to write sulfur trioxide, which is that. All right. 2 nonmetals. We say how many there are, and we never say mono for the first one. So if we write sulfur, that means there's 1. Trioxide means there's 3. Now we have 7.98 moles. of that compound. Let's find out how many oxygen atoms would be in that many moles. This is moles of compound. How about moles of atoms? Moles of atoms of oxygen and compound. So that means this one will cancel. What's the ratio? For every 1 mole of compound, right? We have 3 moles of oxygen. Okay. So now that we've got moles of oxygen, we can convert to number of atoms. And it's the same conversion factor as always. Avogadro's number. Now we can say 7.98 times 3 times 6.022 to the 23rd. And I get 1.44167 times 10 to the 25. Okay, we got 3 significant figures, 1.44 times 10 to the 25th. Atoms of oxygen. In that many moles of compound. Okay, so that would be B. B is your answer. All right. Number 49. Four molecules of chlorine weigh. All right, notice in the answers we have two different units. Grams and atomic mass units. Notice also that they're claiming that possibly 4 molecules of chlorine weigh 284 grams. Is that reasonable? No, it's not even reasonable. So I would look for atomic mass units first. So 4 molecules of chlorine molecules, 4 molecules of chlorine, which is diatomic. So how much does a molecule weigh in atomic mass units? Well, 35.45 is for each one. So we need 2 of them. So that's, let's see, and 189, and then 10, and then 7. 70.90 atomic mass units. 70.90 AMU per molecule. So 4 times 70.90 is, this is a counting number, so we can keep as many of these as we want. I'm going to round it off to the nearest whole number, 84 atomic mass units. And that's C. We saved ourselves a lot of work. We didn't have to calculate grams because 284 grams and 142 grams is not plausible for individual molecules of chlorine. All right. We have 53. All right. Which represents the greatest mass? Okay. Iron, aluminum, rubidium, titanium. We have 1 mole of each one. So we just compare the molar masses of each element. And we know that they're not all the same. They're the same number of moles, but we know from the periodic table that they're not going to be the same. So A cannot be an answer. Right? Right? That can't be. So we have iron, aluminum, rubidium, and titanium. And 1 mole of each one. So we just look at the periodic table and find out what the molar masses are. Iron is 5585 grams for that mole. And aluminum is 2698. Rubidium is 8547. And titanium is 4787. That's easy. Rubidium has the greatest mass for 1 mole. $61. All right, a sample of metal weighing 2.59 grams is combined with oxygen. So our metal is 2.59 grams. We're given that. Combined with oxygen. The metal oxide weighs 3.01 grams. The metal oxide, and we must have something else. The mass percent of oxygen in the compound. Oh, okay. Whatever this combination is, right? We don't even know what the subscripts are. But we know the amount of metal is that much, and the compound is 3.01. Can we answer that question? Well, this is the metal, so what's the oxygen? Right? The oxygen is the difference between those two. Which is 0.42 grams of oxygen. Now that we know that, we can ratio that to the total and find out what the percent by mass for oxygen is. And that's 3.01, but is 13.95349%. Or two significant figures, 14%. Okay, best answer there is E. All right. The next one is like one we've done before. It's just a bigger molecule, nitroglycerin, 62. So nitroglycerin is C3H5, C3H5, and then 3 nitrates. That. So all you have to do to determine the molar mass of this molecule is just 3 times 12.01 for that carbon, 5 times 1.01 for that hydrogen, 3 times 14.01 for the nitrogen, and 9 times 16 for the oxygens. Okay, and your answer should be 227 grams per mole. Okay. 63. certain compound has an empirical formula of NH2O. NH2O. That's the empirical. Okay. Its molar mass is between 55 and 65. So the molecular weight is between, what did I say? 55 and 65. 55 to 65 grams per mole. Okay. We know this is the empirical. Then the molecule is going to be this. So what's the empirical weight? Well, it's 14.01, 2.02 for the hydrogen, and 16 for the oxygen. Well, 3203 grams per mole of that formula. And we know that N has to be a whole number. So if it's 1, that doesn't put it between these two values. If it's 2, then we get about 64. That's good. So 2 is this value, and we have N2H4O2. That's why the answer is B. Okay, 64. The molar mass of blood sugar, C6H12O6, is also known as glucose and dextrose, is what? I'll say. Okay, so we have C6H12O6. You just say 6 carbons, 12 hydrogens, and 6 oxygens. And add them together, you should get 180.16. Okay, just that simple. Determine the percent composition by mass of lead in PbF2. And that's 67. PbF2. We want the percent by mass of lead. Okay. Are those the correct symbols? Yeah. Pb is lead. F is fluorine. Percent composition. So we need lead is 207.21. 207.21 is just one of them. Then we have 207.21 down here, plus 2 times 19 for the fluorine. That's how you calculate percent composition. And it should be 84.5, yeah, 5%. Okay. Let's see, we're going to skip a few repetitions. This is a repetition also. Sort of. We went one direction for this water problem, and this one goes back the other direction. Calculate the number of moles of water in 72 grams. So 72 grams of water. We need to convert to moles, and the magic number is 18.02 grams. Why? Because water is 2 times 1.01 and 1 times 16. Just add them together, and that's what you get. And we should end up with 4 moles. Now, we haven't been doing this explicitly, but does that make sense? Right? Approximate. What's 4 times 18? Well, 2 times 18 is 36. And 2 times 36 is 72. So yeah, it's exactly 4. All right. $77. What's the percent composition by mass of oxygen in Li2SO4? Which is what? Well, is that correct? SO4 is a polyatomic ion with a 2- charge. Lithium is an alkali metal, which is always +1. So yeah, that's correct. Now it depends on whether this compound is in water or not. No, it doesn't. Excuse me, my mistake. We just name it lithium sulfate. But to answer the question, we want the percent composition by mass. So we need oxygen in the numerator. We need 4 times 16. And we also need 4 times 16 in the denominator because it's part of the whole. And then 2 times lithium, which is fairly light element, 6.94 times 100. And if we do our math correctly, we should end up with 58 to 1%. Okay. Oh, my mistake. That's incomplete. What did I leave out? Oxygen, lithium, sulfur. There we go. Now that should be 58. For the percent by mass of oxygen in that compound. I better calculate that to be sure. Some of these problems are not correct. 64 and 6.94 to 2 plus, and then 32.07 plus, and divide that in. Yeah, that's correct. All right, 77. $78. A compound is analyzed and found to contain 12.1% carbon, 16.2% oxygen, and 1.7% chlorine. Calculate the empirical formula for this compound. Okay. Yeah, we'll go ahead and do this one. Carbon, oxygen, chlorine. So carbon, oxygen, chlorine, and then the percent by mass is 12.1%, 16.2%, and 71.7. Okay. We have to get to grams, so we assume a 100-gram sample. That means 12.1 grams, 16.2 grams, 71.7 grams. Now we can convert to moles and get the mole ratio, which is what the formula tells us. The formula of a compound tells us the mole ratio, or the numbers of atoms of each element in the compound. We can't do it with mass. It has to be moles. All right, carbon is 12.01 per mole. Oxygen is 16 per mole. And chlorine is 35.45. Okay. We get these numbers, which are not going to be exactly whole numbers yet. This is 1.007, 1.007 moles. This is 16.2 times 1.013. Okay, those are very close together. And then 71.7, 35.45, and that's 2.022. All right, we can save ourselves a whole lot of trouble. At this point, we're trying to get close to whole numbers. These numbers are extremely close to their whole numbers. So this is approximately 1, 1, and 2. So the empirical formula should be COCl2. All right. For 83. You have 12.6 grams of an unknown substance A and 35 grams of chlorine gas. Okay, we have A is 12.6 grams. 12.6 grams of A. And I have 35 grams of chlorine gas. Okay, that's given. Substance A contains 1.5 times as many molecules as chlorine gas. The number of moles of chlorine. It should be 2 times 35.45. Okay. So we have 35 enter and 35.45. 2. So we have 0.494 moles of chlorine gas. Okay, now this one has twice as many moles as that one. 1.5 times, excuse me. So 1.5 times that value gives us the number of moles of A. 0.740 moles of A. Okay, now we have moles of A and grams of A. So grams per 0.740 moles equals what? 12.6 is 17.02. And we have these to select from. Uranium fluoride. Uranium is a massive element. Uranium is 238 grams per mole, right? So it can't be uranium. Right, we can just cross that one out immediately. How about oxygen? Well, 2 oxygens is 32, right? That's not it either. Right, 16 for each one times 32. Ammonia is 14.01 plus 3.03, which is 1704. All right. I think we got a winner. Right? Boron trifluoride. Fluorine is 19, so 3 times 19 is way too big. All right, we can eliminate that one. And carbon monoxide is 12 plus 16, which is greater than 17. So we found our answer. Ammonia is the compound. '88. What's the percent composition by mass of magnesium in this compound? All right. This is fairly simple, right? Magnesium. ASO4 is arsenate. ASO4. And that should be 2, yes. Because this is a 2 plus, and this is a 3 minus. So we take the 3 over here and the 2 over there, and that gives us the correct formula. Magnesium. Okay, so we need 3 times magnesium, which is 2431. Then in the denominator, we have 3 times 2431 and 2 arsenics. So we look up arsenic and find it's 7492. Okay, and that's 2 arsenics and 8 oxygens. Okay, if we do our math correctly, we should get 20.8%. Magnesium by mass. Okay. And 91. Let's see what 91 has to offer. The compound is composed of element X and hydrogen. Okay, so we got X and hydrogen. We don't know what X is. Is it a metal or a non-metal? We don't know yet. Analysis shows that the compound to be 80% X by mass. So it's 80% X by mass, which means hydrogen has to be 20% by mass. Okay. 3 times as many hydrogen atoms as X. So we have 3 times as many hydrogens as X per molecule. Which element is X? Well, this could be 2 and 6. It could be 3 and 9. But the ratio is going to be fixed. Even if this is in the empirical formula, we should still be able to determine what X is. In order to determine what X is, we need, we can't find number of protons, the atomic number from this, but we might be able to get the molar mass. So we need X grams per mole. Okay. How do we get this value? We get a certain mass, and this is not the same as X. This is X grams of X. Then we have this many grams of X, and we have the rest of it is, and this is due to the molar mass of X. This is the contribution from the hydrogens. And that's equal to 0.80. I'm using the decimal instead of the percent. So if we solve this for X, we should be able to find out what the mass of X is. And so we have X on this side, and then 0.80 X on this side, plus 0.80 times 3.03. Okay. So that 0.8 times 3.03 is 2.424. And then we take this 0.8 over here, and that's 0.2 X. Because this is 1 minus 0.8. Right, that's 1 minus 0.8 is this one. Is 2.424. What X is mass. So, and that's mass for 1 mole. So we're doing this for 1 mole of the compound, and that's 1 mole of X. So if we find the mass here, that's the mass per mole. 0.2. X equals 2.424 divided by 0.2. There we go. 2.424 enter 0.25. That's 12.12.12 grams. So 12.12 grams per mole. The closest one to that in the periodic table is carbon. Okay. All right. What do we got left? 94. Let's see. I got a half hour. We should have enough time. You have two beakers on your lab table. Beaker 1 contains 32.07 grams of sulfur. Beaker 2 has 74.92 grams of arsenic. Which beaker contains the greatest number of atoms? So we have beaker 1, beaker 2. The one on the left, beaker 1 has 32.07 grams of sulfur. And beaker 2 is 74.92 arsenic. And the question is, which beaker contains the greatest number of atoms? And then there's an explanation on it too. So how do we determine the number of atoms? We just find out how many moles. So sulfur has 32, molar mass is 32.07 grams per mole, right? That's 1 mole of atoms. Arsenic is 74.92 grams per mole. So that's 1 mole. So they each have 1 mole of atoms. All right. So A says beaker 2 has more atoms. That's not true. Beaker 1 and 2 for B contains the same number of atoms because there is 1 mole in each. We found our answer. They're not different. They're exactly the same. So B is your answer. 97. Convert 4.13 moles of PCl5 to molecules. Okay. 4.13 moles. And remember, it doesn't matter. We're already in numbers, so we don't need to know what the molecule is to convert to the number of molecules. We just need the correct conversion factor. (6.022 times 10 to the 23rd per mole. So that's going to be about 24 times 10 to the 23rd, or 2.4 10 to the 24th. D would be your best answer. Okay. I got that answer by estimating. I didn't use the whole number. I just said, what would 4 times 6 be? It'd be about 24 times 10 to the 23rd, and then convert that to scientific notation. I'd move the decimal 1 and put it in the exponent, and that's where I get 2.49 10 to 24. And I can mark that answer and move on to the next one. (5.392 grams of hydrogen gas contains what? We've got atoms, molecules, and atoms of oxygen. Okay, 5.392 grams of hydrogen gas. First, we want to convert it to moles. Okay. Hydrogen gas is going to 2.02 because hydrogen is diatomic. All right, so our first estimate is 5.392. Enter 2.02. Divide is 2.67 moles of H2. Any of those 2.67 moles of H2? No. Okay. How about atoms of hydrogen? Well, let's see. Are there any others that are moles? Atoms, hydrogen atoms, molecules. All right. It won't be 5 atoms. This many moles is going to be huge. We could convert it to molecules, right? 6.022 times 10 to the 23rd times that value, which is about 1.61 times 10 to the 24th molecules of H2. 6.1 and molecules. No. The one that says molecules, either one of the molecules is wrong. B and C are wrong. A is wrong. So how about hydrogen atoms? Well, there are 2 hydrogen atoms for each molecule. So 3.22 times 10 to the 24th atoms of hydrogen. There it is, D. So we had to work our way down the line until we found one that matched our answers. 100. Consider equal mole samples of dinitrogen monoxide. Okay. Aluminum nitrate. Yeah. And potassium cyanide. So we got equal moles of each one of these. Rank them from least to greatest number of nitrogen atoms in each sample. If we have equal mole samples, say we have 1 mole of each. Okay. Least to greatest number of nitrogen atoms in each sample. Well, how many moles of nitrogen are in this one? Well, 2 moles of nitrogen. This has 3 moles of nitrogen, and this one has 1 mole of nitrogen. From least to greatest, the first one is potassium cyanide. The second one is laughing gas, and aluminum nitrate is the last one. So E would be your answer. That was fairly simple. How about 101? Calculate the mass of 3.53 times 10 to the 3.53 times 10 to the 26th atoms of silver. And we want to know the mass. All right, that many atoms, we have to convert to moles first because we can't get there with this value. So we need atoms on the bottom, moles on the top, and that's 6.022 times 10 to the 23rd. And now we can do moles to grams. So silver is 107.87. 107 0.87 grams. Cancel moles. Now we have mass. And if we do our calculations correctly, we should get 6.32 times 10 to the fourth grams. All right. Yeah. Or 63 kilograms. That's a lot of silver. I wouldn't mind having that much silver at today's prices. 106. The mass in grams of 3.52 moles of nitrogen. Moles of nitrogen. So we can go from grams to moles. All we need is the molar mass of nitrogen. You know that nitrogen is diatomic. So this is 28.02. Okay. And if we do our math correctly, we should get 98.6 grams. Is that reasonable? Well, let's see. 3 times 25 is 75. And then a half of 25 is about 12. 8. Yeah, that's close. Estimating. 110. Go. Calculate the molecular formula of a compound with the empirical formula CH2O. That's the empirical formula. And a molar mass of 180 grams. So the molecular weight is 180 grams per mole. I should have put a period after that. Give us 3 significant figures. So we need to know that number right there. Well, the empirical weight for this one is 12.01 plus 2.02 for hydrogen and 16 for oxygen. So that's 3, 0, 8, 10, 2, and 3. See if I did that right. 3, 0, 4, 10, 1, 2, 3, 30.03 grams per mole. So now all we have to do is ratio the two. Well, it's approximately 6, right? 30 times 6 would be 180. So if that's equal to 6, then our formula should be C6H12O6. Oops. Well, that looks like glucose. All right, 113. A 60.2 milliliter sample of mercury contains how many atoms of mercury? 60.2 milliliters. 60.2 milliliters of mercury. And the question is, how many atoms? All right. This is a multi-step dimensional analysis problem. We need to go to number of atoms. But in order to get there, we have to find out how many moles of mercury there are. We can't go from milliliters to moles, but we can go from milliliters to grams. With the density, 13.6. Right? Now we can go from grams to moles. We just need the molar mass of mercury and look it up on the periodic table, 200.59. Okay. Now we can go to atoms with Avogadro's number. Okay. And if we do our calculations correctly, we should get 2.46. Yeah. times 10 to the 24th atoms. Okay. We ended up with the correct units there with our conversion factors. Okay. 116. Let's see, how many do I have to go? 116. Oh, that's the last one that I have highlighted. Vinegar contains carbon, hydrogen, and oxygen with percent mass of 40.01% carbon. Carbon. 6.7% hydrogen. And the rest is oxygen, correct? So what would the rest be? Well, let's find out. It's got to add up to 100%. So 100 minus 40.01 minus 6.7 is 5.3. No, 53.29. There you go. That's the trick to this one. If the molar mass of vinegar is 60 grams per mole, what's its molecular formula? You should already have this one memorized, but this is how you calculate it. Assume a 100-gram sample. Now we can convert to moles. Okay. Oxygen is 16 per mole. Hydrogen is 1.01 per mole, and carbon is 12.01. Okay. So we'll do a little number crunching. And 12.01 divide, I get 3.33. Okay. 6.70 divided by 1.01 is 6.63. Okay. And 53.29 divided by 16 is 3.33. Okay. If we divide through by 3.33, what are we going to get? This is going to be 1, this is going to be 1, and this is going to be, well, 1.99, which is about 2. So our ratio of carbon to hydrogen to oxygen is 1 to 1. Now we need the multiplier. What's the empirical weight of this compound? Well, it's 12.01, 2.02, and 16. Right? That's 30.03. So 30.03 divided into 60 is about 2, equals 2. So the molecular formula is C2H4O2. Okay? Now, when you write vinegar as an acid, actually, when they say vinegar, they're talking about acetic acid. Acetic acid would be HC2H3O2. Take one of these H's out here. This is the acidic hydrogen, and this is the acetate ion. Okay. That's the way we would write acetic acid. But this is the molecular formula. All right, that's it. I don't have any more labeled, any highlighted. A lot of repetition. Notice that excuse me, there. Useful information, also polyatomic ions. These will be available on the test. And periodic table, I should have an updated version of the periodic table, but yeah, this one would work because you're not going to need any of these transuranium elements, they call them. Okay, that's it.